Okay, so thanks especially to the organizers for organizing this meeting and then this chance to speak about some of the work that I've been doing. So today I'll talk about the scission of polymers in turbulent flows. So this work has been done, with Dario, Emmanuel, Samriddhi, and Takeshi. I think to many of us, these are familiar faces. So I think Dario is giving a talk tomorrow. All right, so since I'm going to be talking about polymers and flows, I cannot but start with the famed Tom's effect. So here is a relatively recent visualization of this effect, the Tom's effect, or the drag reduction effect. So if we start with a Newtonian channel flow, which is what you see on top here. Sorry, let me just turn my pointer on. Yes. So if this is just a visualization of the vorticity at the bottom wall of a turbulent channel flow. And then you start adding in a bit of polymer, which is represented by this Weissenberg number increasing. And as is well known, if you start even with a little bit of polymer, which can be stretched by the flow, then you see this dramatic effect on the vorticity structures and other structures in the flow, which a zoom in is shown here, right? So you can see these hairpin vortices get destroyed progressively as the flow becomes more viscoelastic. And the consequence is a reduction in the turbulent drag. So this picture shows it, I think, quite nicely schematically, that if you have a fixed pressure drop and you add in some polymer, what ends up happening is you get a higher flow rate. So by the way, these are simulations of the Fini-P continuum model. But of course, there have been many experiments which have seen this effect, and I'll be showing one later in the context of Scission. Okay, they are going to the other end of the Reynolds number spectrum. There is the equally interesting phenomena, though more recent, of elastic turbulence, which has been studied by Steinberg's group. So here's one of the many experiments that his group has done. So if you have a microchannel where the Stokes number is again, the Reynolds number is small, the flow is almost Stokesian. And so you have this kind of serpentine channel and you have fluid flowing through it in which you can introduce polymers. And what's done here is you have a dye from one side and clear water on the other. And without polymer, you see that there is very little mixing. So the flow is laminar. And then, when you introduce the polymers and they're sufficiently elastic, then you introduce chaotic fluctuations and this dye gets well mixed. And note the small Reynolds number. There are also earlier experiments than this done in this kind of rotating co-ed geometry. And, this was in fact, I think, one of the first papers that showed this. Okay, so the point in both these initial slides was just to emphasize or recall the fact that when you have a small amount of polymer in a flow, you generate, the polymers can get stretched out by the flow and, go and relax back and exert a feedback force onto the flow and modify the flow at a very basic level. So the flow structures change at the smaller scales of the polymer, and then this feeds back onto the entire flow, and you can have global changes like in the total drag reduction. Now, central to this is the fact that the polymers are being stretched. A counterpart to that fact is now if the polymers are being stretched, there comes a point ultimately where the force on them exceeds some threshold and they actually break. So they mechanically undergo a mechanical scission and the polymer breaks up. And what this means is that the effective molecular mass of the polymers you have introduced degrades in time till you reach a point where these small fragments can no longer stretch, and therefore you lose the interesting phenomena that you wanted to investigate when you put in the polymers. So this is something that is unavoidable in experiments, because you can imagine if you want the polymer effect to be significant, either they should be highly elastic so that they can really stretch, or you crank up the Reynolds number, or you crank up the flow strain rate. but then that eventually causes them to break. So this is something you cannot avoid in experiments, but when it comes to modeling, this is something that's been typically ignored with good reason. The problem is quite complex to understand even without this phenomenon. But it's something that this is what we want to study. Okay, so let's look at experiments where this has been seen, this mechanical scission and loss of drag reduction. So this is one of the early experiments that saw this effect. So once again, it is flow in a channel, and we have two different types of polymers being introduced here. And what's being plotted here is the friction factor versus the Reynolds number. The Newtonian result is this top curve, which is just the Blasius equation. And then when you add polymer, you get this reduction in the friction factor, which is the drag reduction. Now, of course, this is the maximum drag reduction asymptote, which we cannot cross. So what happens is, as you increase the Reynolds, for a while you go along the MDA, but then you reach some value of the Reynolds number beyond which, if you keep increasing it, the polymers start to break. And as a consequence, the viscoelasticity is lost, and the drag reduction starts to reduce, and you start going back towards the high value of drag in the Newtonian flow. And you see, if you have more polymer, this effect in some sense gets delayed, which is understandable. So this is really a signature of scission, right? That you lose the drag reduction. Let me show you another experiment. So the earlier one was in a pipe where you have, in a sense, a fixed residence time. So for it to break, you really need to go to higher Reynolds number. So you have more strain in a given residence time. But another way of looking at this is you do an experiment where it's a closed experiment, so you can run it for long times. And now, even at a fixed Reynolds number, if you wait for long enough time, you see that the polymers degrade. So again, here you're directly seeing the drag reduction being plotted. These are experiments by the group of Suarez. So you see that initially at early times, it takes a while for the polymers to get stretched, and then the drag reduction comes into play. You reach a peak, and then if you wait long enough, the polymers degrade and you lose the drag reduction. Note the logarithmic scaling of the time axis, right? So it's actually very quickly that you get the full drag reduction out of the polymers, and then over long times, this polymers degrade. Okay, so that was by way of experiment. So this has been known for a while. The problem is that it's quite challenging to model scission or to include scission in numerical simulations. So here is one of the first valiant attempts, again by Suarez's group. So what they've done is introduce scission into a continuum model in a sort of ad hoc phenomenological way. So they've essentially made the maximum length of the polymer in the Fini-P model degrade in time, again, in some kind of, ad hoc fashion. And what they're able to get from there is, so this blue curve is the degradation of the length. You can see you see how it goes down, and consequently, they do get a loss of drag reduction, but quickly there are these kinds of non-physical numerical instabilities. So this is one problem with the model, and the other is, of course, that this is a purely ad hoc sort of way of introducing it, and there are other issues when you look at details. So what we really need to do to get a sort of consistent prediction of this scission effect is to understand what's happening to individual polymers in the flow. Because after all, scission is something that happens at the scale of the individual molecule when that individual molecule hits some threshold of force. And it's hard to see how one can coarse grain this, without having some detailed understanding of individual polymer dynamics. And I would say that this is just one of a prominent example of where we need more understanding of individual polymer behavior to improve continuum models going ahead. So that's the focus of the talk, looking at individual polymers to try and understand scission. But before I go to scission, I thought it would be nice to just summarize what we know about the stretching of individual polymers in turbulence. And also just to highlight that the utility of random flows as a tool to study this problem. Okay, so let's look at polymer stretching, but first in laminar flow, where it was first kind of studied experimentally. So, and also theoretically. So you see, this is the experiment by the group of Perkins, Smith, and Chu in Science, where they put a polymer inside this cross slot geometry, and you can nicely see it through fluorescence imaging how the polymer stretches out due to the flow. And if you plot distributions of the polymer extension, you see that it's initially peaked at small extensions for small Weissenberg. Oh, so I should say that here the Weissenberg is a ratio of the relaxation timescale of the polymer, which is tau, to the timescale of the flow. In this case, is just the inverse a strain rate at this center point. So that's 1 over gamma. So now if you increase the Weissenberg, or in other words, you increase the amplitude of the strain rate in the flow, or you take a polymer that's more elastic, then you see that all the polymers stretch out. So these are just like ensembles represented as a PDF. And so what's important to note is that there is a peak that sort of shifts to large extensions. And if you look at the mean of these distributions, you also see this dramatic stretching out. And this is what was termed the coil stretch transition. So how can we model this sort of phenomena? So let's just say something, look at standard models for polymers. So a simple mesoscopic sort of model is to look at a bead spring chain. So this is a well-known, a bead spring chain model for polymers, where what one does is sort of represents the effect of the flow on the polymers and their feedback via beads. And the entropic relaxation of this molecule is captured through springs interconnecting these beads. So you have this bead spring chain represented here. And so this is the classic Rouse model, if one ignores hydrodynamic interactions and extruded volume interactions. So these are the equations that we get if we have an n-bead chain. So you have the equation of motion for the center of mass, which just moves with the velocity sampled by the center of mass of this chain. And then you have white noises applied on the beads to represent the effect of thermal forces from the solvent. And then we also complement this with the equations for the interbead separation vectors, QIs. So the first term here represents stretching by the background gradient. Throughout, we will be assuming that the polymer is much smaller than the Kolmogorov scale of the flow. So at the scale of the polymer, the background flow is linear. And therefore, this term is sufficient to represent the strain. It's just the Taylor expansion, first term. And then you have relaxation due to the spring forces and the effect of noise. So maybe the other detail I should mention is that these forces typically are Finney springs. So we have a maximum extension of the spring. One can include, it's not here, but you can add extruded volume and hydrodynamic interactions. And I'll say a little bit about that later on. But at the first approximation, we will ignore it. Now we can define the Weissenberg number here by taking the timescale of this chain, like the longest timescale. Of course, there is a spectrum of timescales here if we have n beats because of different modes. But we take the largest one to be the timescale, and that's what's done when you define it in experiments as well. And then the interesting thing is we can estimate, I would say, the effective timescale of the entire chain from the timescale of individual springs using this relation. This relation was proposed by Jin and Collins. It's sort of it's an educated guess. Let's say I'll talk about it more as we go along the talk. But this is the definition of the Weissenberg now. Okay, so let's come back to the stretching in an extensional flow. So this was the experiment that I showed you first. And if one does simulations of these bead spring chains or even a dumbbell, you can recover this basic phenomenology. So at small Weissenberg, everything is peaked at small extensions, and then it undergoes the coil stretch transition. The key thing to note is, except at the transition, you always have this kind of narrow peak. So all the polymers kind of coherently go from being coiled to being stretched when you're in laminar flows. This is an important point because I'll contrast it later to what happens in chaotic and turbulent flows. Okay, so that brings us to now stretching in turbulence. So it was not so obvious in the beginning, I mean, in the early years of this work, whether of this area, whether polymers actually will get stretched out in a turbulent flow or not, because if you can imagine a polymer inside this kind of flow, which is, these are, by the way, dissipation structures, intense dissipation structures. So a polymer moving through this flow will feel a fluctuating dissipation rate and therefore a strain rate. And then the question is, how do we know whether it's going to get stretched out in the long time average? Now, this is clearly something that can be tackled through dynamical systems ideas, and that's what was eventually done. So you look at if we think of the polymer, if we think of an material line element advected along the flow, then we know that if the flow is chaotic, this thing is going to grow exponentially in the long time following the Lyapunov exponent, and defined in the usual way. And so it becomes natural to think of the Weissenberg number now as a ratio of the time scale of the polymer to the time scale of the flow, where now that time scale is just the inverse Lyapunov exponent. And then you can imagine that if the Weissenberg number is greater than 1, certainly these polymers should stretch on average, or should have stationary statistics that involve extended polymers. A more precise description was given in this seminal work in PRL, where if you have, they started with the generalized Lyapunov exponents, right, which is just this definition, but the qth moment of the stretching. And if you have these Lyapunov exponents for your given chaotic flow, then if you take a dumbbell, the simplest model for a polymer, and you can show that, or as they showed, that the probability distribution has a power law tail, which goes as -1 minus alpha. And this power law exponent alpha can be simply determined in terms of the generalized Lyapunov exponents. And of course, here, this is the Lyapunov exponent here, and this is the Weissenberg number. Now, to make this more concrete, we can take possibly the simplest, okay, I should not say that, but we can take an example of a random flow, which is a simple model for turbulence, which is just a random Kristian flow in the Batchelor regime. So it's a Gaussian gradient that is incompressible and isotropic. And for that particular flow, the generalized Lyapunov exponents have this quadratic relation where lambda is just the Lyapunov exponent, and 3 corresponds to the spatial dimension. And then you can show that this exponent alpha has this simple relationship for this Kristian flow. And what's immediately clear here is that when the Weissenberg number is half, right, alpha becomes 0. And that means your power law has r to the -1 behavior, which is not normalizable, if you are dealing with the ideal case of an infinitely extensible polymer. So that was found as a convenient way to define the coil-stretch transition in turbulence. Now, if I quickly show you simulations in the same random flow, so you take the Batchelor-Kristian flow, but now you do simulations of dumbbells by evolving those equations for the dumbbell I showed earlier. Then you do get, it's kind of verification of the earlier theory. So you see that as Weissenberg crosses half, you have this transition from being peaked at small extensions to peaked at large extensions. If you look at the mean extension of the distribution, that also undergoes quite a rapid increase around Weissenberg half. And that sort of just reinforces the fact that there is this kind of transition. It's not as sharp as in laminar flows, but it's there, and there are other reasons to call it a transition. For example, you have critical slowing down of the PDF's dynamics near the transition. But yeah, I can discuss that if there are questions later. The important point to note here is you see the distributions are very broad, right? And that's something that we should contrast with laminar flows. Now, there's been a lot of work done on polymers in the Batchelor-Kristian flow, and here are some references. People also then naturally looked at doing simulations in, quote unquote, actual turbulence using DNS. And different turbulent flows were looked at, shear flows, 2D flows, turbulent channel flows, and the closest thing to the Kristian flow, the 3D isotropic box turbulence. Without going into details, in all cases, the basic features remained the same, that you had power law tails, and the exponent of the power law increased as you increase the Weissenberg number. And so you can have something like a Coil-Stretch transition where the mean extension increases dramatically across the critical Weissenberg. Okay, so something we wanted to do recently was to do a direct comparison, right, of the stretching in a DNS in box turbulence with the Kristian flow, to kind of understand how good a tool is Kristian flow if we want to get some quantitative details correct. So clearly, qualitatively, it works well. To some extent, it's not surprising because the theory of the generalized Lyapunov exponents is valid for any chaotic flow. So the details aren't important as far as the qualitative features that you will have a power law that, with an exponent that increases with Weissenberg. But if you want to get the details right, can we come up with a Kristian flow that works well for a given DNS? So what we did is we did simulations of dumbbells in a homogeneous isotropic DNS, and then also synthesized a random Kristian flow by matching the Lyapunov exponent with that of our DNS, as well as the correlation time of the strain and the vorticity. There are different ways, of course, to construct an equivalent random flow to turbulence, and this is what we chose in this case. And then this is the comparison. So the solid line is our DNS dumbbell simulation. The dotted line is the dumbbells in the Kristian flow. The dashed line is a 10-beat chain in the DNS. For the moment, forget the dashed line. Just look at the solid line and the dotted line, right? And this is the probability distribution of extensions. And you see that it does quite well. At small Weissenbergs, it seems like the DNS stretches the polymers more. So that's somewhat what we expected, because the DNS, of course, has these extreme stretching events that won't be there in a Gaussian flow. But rather surprisingly, at high Weissenbergs, for example, the green curve and the red curve, we found that the Gaussian flow was actually stretching it more. And I'll discuss about that in a second. Before that, the other interesting thing to note is that the 10-beat chains, which is the dashed line, also showed similar results. So that shows you that the dumbbell actually works quite well, and at least for these kinds of basic behavior. And the simplest case of a dumbbell in a random flow, does quite well even quantitatively. So that will be useful for our Scission work in a second. So now if I extract these power laws from these PDFs and just plot them versus Weissenberg, this is what we get. So the red symbols, the red markers are from our random flow, and the blue markers are from DNS. And you see this emphasizes what you see here visually, that at small Weissenbergs, the DNS, the flow stretches out more, the polymers stretch out more. They have, power law exponents that are higher at small Weissenberg. Whereas at large Weissenberg, the random flow actually stretches out the polymers more effectively. And the transition happens at the coil stretch transition. So maybe briefly, I'll just talk about this before going on to Scission. So the question of how does a polymer respond differently to DNS and a Gaussian flow, where the chaotic Lyapunov exponent has been matched, is equivalent to asking what is the effect of extreme stretching events on polymers. Right. So here I've tried to pictorially depict the PDF of this dissipation, right, which is like a stand-in for the, let's say, strain rates that will be experienced by the polymer in the two types of flows. Sorry. So the red curve is typically what one would see in a DNS. This is not our DNS. This is from the paper Watanabe and Goto. Unfortunately, I didn't have the time to make this PDF comparison. So instead, I resorted to this just for this illustration. So typically in a Gaussian flow, you'll have this log normal type of dissipation PDF. So sorry, in DNS, you'll have this log normal dissipation PDF, which is the red curve. And then our Gaussian, which we matched, the Lyapunov exponent and correlation times, looks like this black line. And I drew this black line by hand, and I'm quite proud of it. I think this last year of online teaching has helped me. So anyway, excuse me for this freehand drawing, but this is the Gaussian curve. So what I would like you to note is that although the Lyapunov exponent is matched now, the DNS has extreme events that the Gaussian flow does not have, as you can see in the tails. In contrast, right, the Gaussian flow has more abundant mild stretching events, right, which is what you can see in the core. And that's the key to understanding what's going on here. So a simple physical picture is that at small Weissenberg, when the polymers do not want to stretch, right, they're very stiff, they don't want to be stretched. There, it's really important to have these strong stretching events that the DNS provides. That's why at small Weissenberg, the real turbulent flow is able to stretch out the polymers more than the random flow. On the other hand, when the Weissenberg is large, right, that's like you have a large relaxation time. The stretching now, in some sense, can sample a long history of strain rates. And under such circumstances, a mild but persistent straining can be as, if not more effective than short-lived strong stretching. To make this quantitative, we did the following. We did a persistence calculation on, basically we try to look at how long does a polymer stay stretched, or what is the persistence time of a polymer in a stretched configuration. And can we detect this feature, that are they stretched more persistently in the Gaussian flow? So we defined the time of stretching as the time spent in a stretched configuration, which we defined to be as when the extension is greater than 50 times the equilibrium extension. The maximum extension in our Fini dumbbells are 100 times the equilibrium. So it's far away so that it's not being affected by these nonlinear effects. And this is what we see. So this is the PDF of the time it stays in a stretched configuration. So at small Weissenbergs, they're pretty much the same. I should mention that the dashed line is the Gaussian Kristian flow. The solid line is the DNS. So it's pretty much the same at small Weissenberg. So the polymers collapse so quickly that it doesn't really sense these differences in the flow. But as you increase the Weissenberg, for example, at Weissenberg 1, where you start seeing that the Gaussian flow actually stretches polymers more than the DNS, you do see that the polymers stay stretched longer in Gaussian flow than the DNS. So they do persist longer in the Gaussian flow. And that becomes more prominent at higher Weissenberg. So this just kind of gave us evidence for that physical picture that polymers behave in this way, where they sort of, their instantaneous extension is a result of a history of straining. And when they are at small, if you have a small Weissenberg guy, that history is very small. So it really needs strong stretching events. Even though they are short-lived, it's fine. But when you have large Weissenberg polymers, which are easy to stretch, they have long relaxation times, then what's more important is to have persistent stretching, and therefore even a Gaussian flow without extreme events actually stretches it out more. Okay, so that was just by way of stretching. Before we end this part, I just wanted to mention that there have been experiments that verified these kinds of power law tails. Of course, they were not done in high Reynolds number turbulence because it's very difficult to look at things smaller than the Kolmogorov scale. So instead, they were done in the chaotic flows that arise at low Reynolds numbers when you have elastic turbulence. And these were all experiments done again by Steinberg's group. And the main point is that he does see these broad distributions of extensions as you increase Weissenberg and the flow becomes chaotic. And he's able to measure the PDFs of extension and see that there are power laws that increase in the way the simulations lead one to expect. So things seem nice and consistent here so far. Okay, so let me just summarize what I've said about stretching, and when it comes to, what are its implications for Scission. So what I want you to take home from everything so far is that polymers stretch very differently in a turbulent flow versus a laminar flow. So if you have a polymer in a laminar flow, right, and you increase the Weissenberg, there is a peak, and that peak simply translates to large extensions. So the distribution is always quite narrow, and you can see that here. In contrast, in turbulence, there is a broad distribution, and it's just the power law exponents that change with Weissenberg. So what this might suggest now is that there will be a fundamental difference in the way polymers break in a laminar flow and in a turbulent flow. In a laminar flow, either nothing will break, and then beyond coil stretch, everything breaks. In contrast, in turbulence, there will always be some finite rate of breakup because you always have this long power law tail. But we might expect, the breakup rate, let's say, to increase significantly or rapidly as you go past the coil stretch transition. Okay, so just to summarize the state of affairs at this point, you have laminar extensional flows where we understand stretching well. People have also studied scission in these flows using pretty detailed models, so that's also quite well understood. In contrast, in turbulence, we have some understanding of this, how polymers stretch, but the problem of scission has not been studied. And in fact, the fact that it's an open question has been very nicely highlighted in this editorial article by Suarez. And the only existing attempt so far has been a continuum model based on an ad hoc inclusion of scission, and that has numerical artifacts, as I had discussed. So that brings us to what we wanted to do, which is to study scission by simulating individual polymers using Brownian dynamics for the individual polymers, and also do the flow with DNS. So this will allow us to break polymers individually when they stretch beyond a certain threshold, and give us a consistent way to predict and understand what's happening as far as scission goes. Okay, so now given this background of our bead spraying model, that's what we're going to adopt for our polymer description. And that allows us a simple way to model breakup. So all we do now is we say that if any of the links in our polymer chain, if any of these links extend beyond a threshold, which we call L scission, then we say that that link has broken and the polymer breaks at that location. There are, of course, more detailed models, more detailed ways one can model scission and its energetics and so on, which have been done in laminar flows. But given the complexity of things right now, we've just stuck to this very simple prescription. So to reiterate, if any of the links stretch beyond a certain threshold, we consider that it's broken. And then the remaining fragments are allowed to evolve further, and we can do multiple breakups in this fashion. Okay, so that's the kind of modeling framework we're using for scission of polymers. The flow is going to be homogeneous isotropic box turbulence, simulated, with the pseudospectral code in the usual way. And we define the Weisenberg using the Lyapunov exponent of the flow, as I explained. Okay, so in the remainder of the talk, these are the stages I'm going to talk about the scission problem in. So first, I will start with passive polymers, meaning I'll just be putting polymers into the flow and not accounting for their feedback. Right? So looking at very dilute suspensions and just trying to understand how the polymers break up under the influence of the flow. So passive polymers, and I look at only the first scission initially. So I just want to study the statistics of the first breakup event. So first scission. Once we understand that, we look at how a polymer can undergo multiple breakups, right? So after the first scission, we let the daughter fragments evolve further and track subsequent breakups until we reach just individual beads, which you can think of as, fragments that can no longer stretch. And then finally, we look at feedback. So we'll allow the polymers to feedback on the flow and see if we can recover this phenomena of the loss of drag reduction due to scission. All right, so let's start with the first scission event. And let's start with the simplest possible model. So instead of taking an N-bead chain, let's take a dumbbell. I already showed you that the dumbbell works quite well. I'm repeating that here. So the solid lines are the dumbbell, the dashed lines are 10 bead chains. And you can see these are the stationary PDFs of extension are quite close. There is a mapping that has been used. So the question is, if you have a 10 bead chain, how do you represent it as a dumbbell? So that was the mapping proposed by Jin and Collins. I'll talk about that a bit later, but there is a clear way of doing this. So this is the mapping. I'll talk about it later. The other simplification we can make initially is to replace turbulence again by the random Kristian flow, which, as we've seen, provides a very good model. And even the deviations due to extreme events are rather mild. So this is quite a good approximation as a first step. So we replace the true velocity gradient with the Gaussian isotropic incompressible gradient. and we match the Lyapunov exponent as well as the correlation times. Oh, sorry, right now we just match the Lyapunov exponent because I'm taking a delta correlated random flow. Okay, so the benefit of doing that, taking a dumbbell, that to a linear dumbbell, so I neglect the any p for the moment. So I take a linear dumbbell in this delta correlated random flow. The benefit is I can write down a Fokker-Planck equation for the probability distribution of the extensions as a function of time. And this is what the equation looks like. This linear operator is an advective diffusive operator, and it has the Weissenberg number sitting in there. This REQ is the equilibrium extension of the polymer due to the thermal noise. So one thing I should mention here is if we assume the scale separation that the maximum extension is much larger than the equilibrium. In this case, there is in fact no maximum because it's a linear spring. Then we can make this power law ansatz, and what you will find from this Fokker-Planck equation by looking for the steady state PDF is that you get the prediction of alpha to be identical to what we have from the theory based on generalized Lyapunov exponent. So that's consistent. Okay, now let's return to this equation and look at the scission problem. So how do we model scission in this context? We do that via a boundary condition. So at 0 extensions, we just have a reflecting boundary condition. But when the extension reaches the scission length, we set the probability to 0 because any polymer that reaches there essentially breaks up and is no longer polymer because we are just considering a dumbbell here, right? So there are no daughters, they just give you beads. So the probability is 0, that's the boundary condition that models scission. Now the nice thing is that this operator with these boundary conditions is term Liouville. It has orthogonal eigenfunctions, which means that I can write P as a sum of these eigenfunctions with exponentials that have the different relaxation timescales associated with them. And then if I want to know the number of surviving polymers at any point of time, I just have to integrate this probability across all R at any given time. Sorry. Yes, and because this P is known as a sum of eigenfunctions, if I want the long time behavior, I just retain the leading eigenfunction, which predicts that the number of surviving polymers which are unbroken should decay exponentially with a timescale TD, right? Which is just the eigenvalue of that eigenvalue problem. So the first sort of qualitative prediction we get out of this linear dumbbell in the Krigman flow is that the number of polymers is going to decay exponentially. Okay, so with that background, there are more things we can do, of course, with this Krigman flow and predict other things. But in interest of time, I'll move on now to actual DNS of turbulence, in which we put 10-beat chains. So I'm going from a dumbbell to chains. I'm going from the Krigman flow to turbulence, and I do the simulations with the scission in place. So when scission happens, I remove the polymer from the flow, and I consider it to be lost. And then I can plot the number of surviving polymers with time. And what you see is a confirmation of the prediction I showed you earlier, that there is exponential decay. And one can extract out the decay timescale from these plots. And you find that decay time decreases dramatically as you cross the coil stretch transition. Now, this is something that we expected from our understanding of the stretching of polymers. So as you go across the critical Weissenberg of half, polymers start stretching out more. And it makes sense that they also break up faster. Quickly, I can compare the dumbbells versus chains. So this is the decay rate, the loss of the surviving polymers in time. The slope is the decay rate for different number of beats. So I have used the mapping to, you can think of this as if I have a given polymer, I can model it with increasing resolution by increasing the number of beats. So what you see is if you start with a dumbbell, qualitatively you get exponential decay, unsurprisingly. And that gets refined as you increase the number of beats, right? Because you are having more time scales of relaxation and you can model things more accurately. The promising thing here is you see the difference in these curves reduces as you increase the number of beats, which suggests a convergence. So if you really want accurate simulations, maybe 20 beats are probably good enough at at this scale of things. But even a dumbbell is fine if you want to just understand certain basic qualitative things. I'll skip some of these details. Okay, another interesting question, from an experimental perspective is to know the location where the polymer breaks up the first time. So what's been seen in certainly laminar experiments is that it almost always breaks up at the midpoint. In turbulence, this is something that's not known, and it's interesting because the polymer experiences so many more fluctuations. So it turns out that if the Weissenberg number is relatively small, 1 and smaller, most of the breakups do happen at the midpoint. So here I'm plotting a histogram of breakups versus the location of breakup. So you see that most of the breakups happen at the midpoint. This is a 10-beat chain, of course. But as the Weissenberg increases, you have a sort of, at large Weissenbergs, you have a spread out of this distribution. And you find that there are more polymers breaking up at all other kinds of locations. So you have daughters which are not just half-half, but 1/4, 3/4, etc. Maybe I can just ask Alessandra, how much time do I have left?
Jason, you have about, let's say, 18 to 20 minutes, and then one time for a quick question,
okay,
or
great.
less if you want.
Okay, thank you. All right, so maybe I'll just, yes, I put my timer on. Okay, so something else. So I had mentioned hydrodynamic and extruded volume interaction. So just to say that we included these features into our bead spring model, and we found that qualitatively things don't change, although quantitatively they do. So the red line is the simulations of free draining chains. So we don't have hydrodynamic interactions, we don't have extruded volume interactions. That's a red curve. The green curve introduces hydrodynamic interactions, and you see that that delays the breakup. I mean, that delays breakup. And then if you include extruded volume interactions, it again makes breakup a little bit faster. And these are sort of intuitive if one knows something that's known from laminar simulations, which is that when you hydrodynamic interactions, if the polymer starts out coiled, right, you can imagine there are these different beads all close to each other. And hydrodynamic interactions sort of screen the beads from the effect of the flow. So they prevent uncoiling, in other words. And you can see that here, I'm comparing the free draining, just one trajectory, which is illustrative. That the free draining chain is the red one. It uncoils, as you can see here. And the a typical simulation with hydrodynamic interactions shows you that it uncoils later. This is, of course, in the same flow. So in time also, you can see that there are more probabilities for larger excursions and eventually faster uncoiling if you don't have hydrodynamic interactions. So this is well known even from laminar simulations, and that explains why it delays scission. On the other hand, clearly extruded volume interactions are going to make the polymer expand out, and therefore it aids scission. This is important. The effect of extruded volume is important when one thinks of beta solvents and non-ideal solvents and issues like this. Okay, so now let's come to repeated breakups, as I promised. So we just saw statistics only of the first event. Now, after the polymer breaks up the first time, you have two daughters which are still in the flow. And it's natural to ask whether these things will break up again, right, and again, and so on. And will there come a point at which they stop breaking? It seems like physically it should stop, because if you start with a certain chain composed of like you have a chain composed of springs. The springs have a fixed relaxation time. And if you break up this thing into a smaller object so that you have fewer springs, that object will stretch less until you reach a point where eventually nothing stretches anymore. This is exactly what happens physically, because as the molecular mass reduces, as the polymer degrades, you lose the elasticity of the solution. So it's important to understand this multiple breakup statistics and to be able to predict somehow the eventual surviving distribution of polymers, because that's what will remain if you wait for very long times. Okay, so let's look at multiple scissions. So this is what we want to do after the first breakup. Try to track subsequent breakups. And yeah, so now this is where I wanted to discuss this mapping in some detail. So as I said, this tau, so this is a mapping that allows us to relate the relaxation time tau of an individual spring in the chain to the longest effective relaxation time of the entire chain as one object. And here n is the number of beats. So what is the origin of this mapping? As I said, it's a sort of educated guess. So it was proposed by Gill and Collins and shown through simulations to work pretty well. And what they did effectively is they looked at the infinite extensional viscosity prediction for a bead spring chain in a cross slot flow. So you take a laminar extensional flow, you put in a n bead chain, and you calculate the extensional viscosity of the solution. So that you get a formula in terms of the number of beads and in terms of this tau. And what they required is that if I change the number of beads, I want to adjust tau such that that infinite extensional viscosity remains the same. So in some sense, you want the response to the stretching response of the object to be the same as I increase the number of beads. So to do that, it turns out that if you increase n, the tau must be reduced so that I get the same effective relaxation time. And the formula that they pulled out of that was this. So the expression for the infinite viscosity is given in this paper by Reist and Tanner. And Gill and Collins said that that viscosity should be constant. And then they get this, this relationship here. So this is the physical basis is this, that in some sense, it's giving you the same response to uniaxial stretching. Of course, why should this work well in turbulence is not immediately obvious, but it turns out to work pretty well. And I just showed you examples of where 10 beads and dumbbells match quite well. So, okay, so that's the background. So we decided to take this and accept this mapping. Now, how can we use this, or how can we understand this when it comes to multiple scissions? So the way to see this is I now have a chain, which is my, let's say, parent polymer is a 10 bead chain. So I have 9 links in it. Each of the links has a timescale tau. So if the original parent has 10 beats, then the effective relaxation time is 10 times 11 by 6, right? So that it's a long relaxation time. If it breaks up into 2 daughters, such that each daughter has 5 beats, you can see that there will be a reduction in the effective relaxation time of the daughters. So this is the main physical aspect we wanted to be able to capture in our simulations. And that's what this mapping does in a natural way. So what I fix in the simulation is sort of the microscopic ingredient, tau, which is the relaxation time of the individual spring that composes my chain. And now every time it breaks at any given chain location, I just break apart the polymer and allow the daughters to continue in the simulation. And the daughters have a naturally reduced time scale, which means they're harder to stretch. And so eventually we'll reach a point where they can no longer be stretched, either because they reach individual beats where I define the relaxation time to be 0, or they reach a relaxation time where the corresponding Weissenberg is less than the coil stress transition, so that it's difficult for them to stretch. Okay, so that is the kind of background. And now we do simulations along those lines. And here I'm plotting the number of surviving polymers of different sizes with time. So the black, so I start with a small Weissenberg, 0.8, relatively small. This Weissenberg is a Weissenberg number defined in terms of the parent polymer, which is the black curve. So you see that the parent polymer has a Weissenberg greater than the coil stress transition. So certainly it should start breaking up, and that's what we see. There's an exponential decay in the number of parents. And as the parents break up, they give rise to a spectrum of daughter polymers, shown by these different colors. So mostly you have 5 beads, right? That's the red curve. This is because most of the parents break up at the midpoint, giving rise to 5 bead polymers. And those 5 bead polymers don't break any further because already the Weissenberg number for the 5 bead based on their local time scale is actually less than the coil stretch. We'll see that in a second. So these things don't break anymore. If I now increase the Weissenberg number of the parent polymers, you see that they break faster. That's the black curve. They give rise to a broader distribution of daughter polymers, which again refuse to break up anymore. But now if I increase the Weissenberg even further, you start seeing that the 5 bead daughter polymers do break up, of course at a much slower rate, and they give rise to further generations. And this carries on. If I go to higher Weissenberg of 4, you see there are several daughter polymers are formed, they break up and give rise to subsequent generations until the simulation is mostly dominated by just dumbbells. I mean, I started with a 10 bead. All right, so this is kind of, something that one might have expected. The interesting thing is you do get, you do reach a stage where they don't break up further. So that would give us the kind of long time saturated population. So the question is, can we predict a priori, right, based on our simple physical understanding, whether can we predict what the size of the daughter will be, which will no longer break? So what is the largest daughter polymer which doesn't break? We can do that by estimating the Weissenberg number of the daughter polymer. So let's say N0 is the number of beads of the parent and N is the number of beads of the daughter polymer. Then if you have the original Weissenberg of the parent on the right-hand side, you can estimate the Weissenberg of the daughter polymer using this simple, right? So it's almost an N square type of scale. So if I now know the Weissenberg of the daughter, all I have to do is ask whether that is less than the coil stretch transition. If so, it will survive. If it is greater than the Weissenberg critical, then it will also break up and give rise to a smaller fragment. So this logic, just to show you that it works, right? If I take this fourth panel here, where the parent Weissenberg was 4, I can estimate from this formula that if for a daughter polymer with 4 beads, the Weissenberg is 8/11, which is greater than half, so it should break. And n equal to 4 does break. That's the orange curve. On the other hand, for a dumbbell, the Weissenberg is smaller, and that is actually less than half, as you can see here. And therefore, I predict just a priori, right, just based on this simple formula, I can predict that the dumbbell will not break. And that actually does happen in the simulation. So you see that this mapping gives us a very convenient way of anticipating what is the largest polymer that is no longer going to break if we wait for even infinite time. So that gives us a way to figure out what are the surviving polymers in the flow. And this is interesting because it allows us to now explain a experimental observation that was made back in 2006. So this is a paper in PNAS by Vanapalli and co-workers. So they had turbulent flow in various kinds of rheological geometries. They verified that the Reynolds number was high enough for it to be turbulent. And they put polymers into this geometry. They've cycled them through this, for example, this cross slot, they put polymers at the inlet, took it out at the outlet and recycled them. And they did this continuously. After every cycle, they took a fraction and they measured the molecular mass of polymers. And they kept cycling them through until the molecular mass stopped decreasing. And they call that the kind of saturated molecular mass. So, the molecular mass of the surviving polymers. And they plotted that versus the Reynolds number of the flow. And what they found is that if you want the size of the, so the molecular mass can be related to the contour length L. So the size of the survivors decreased with the Reynolds number as expected, right? Because at higher Reynolds numbers, that's like saying the Weissenberg is higher. And so the daughters that survive will be smaller. Interestingly, they found a pretty clear scaling that seemed to be universal. So these different markers are for different types of geometry. So cross slot, contraction, expansion, even a Couette cell. And all of them showed the same scaling, which is the solid line. Moreover, the scaling was that of isotropic turbulence is what they suggested, not channel flow. I'll come back to that later if people have questions. What's interesting is that we can explain this scaling. So we come back to the simple argument that we had, right? That if a daughter is surviving, it means its Weissenberg number is less than the critical. And I can estimate the Weissenberg of the survivor based on the simple formula I showed you earlier. So here n is the number of beats, which is a proxy for the size or the contour length. And tau eta is the Kolmogorov time. Tau is the time scale of each individual spring, like I said. I can now relate tau eta to the Reynolds number using usual Kolmogorov phenomenology. And the consequence is that for large enough chains, this numerator is n square. So n square goes as tau eta. And if I follow the usual scaling, it means the L square should go as Re to the minus 3/2. And that's exactly this black line, as you see here. So our simulations provide an explanation for this sort of scale. Okay, I'll skip this in the interest of time. Here we just a word about it. We tried to ask the question, when a parent breaks and forms 2 daughters, do these daughters break up, or do they behave like parents that had 5 beads, or do they have some memory of the fact that they have been born from a breakup event? It turns out that they do, but that if you wait larger than the Lagrangian correlation time of the flow, the daughters forget that they have been formed from a breakup, and they start behaving as if they are the original parents that you see with the flow. This is important because if one wants to model these multiple scission events in a simple way, this is basically telling you that you can model the breakup of daughter polymers using statistics you have for parent polymers of the same size. I can discuss this further if people have questions later. Okay, so now let's come to the last part, which is where we include feedback from the polymers onto the flow and see if we can recover drag reduction. So I'll skip this slide in the interest of time. Yeah. So what we do is we continue to do the same simulations of, now it's only dumbbells, of course. So we restrict ourselves to Fini dumbbells, and they are seeded into the flow and evolved with the flow. In addition, we compute this. So this is really Takeshi's simulations. So he computes this polymer stress tensor based on the locations of the dumbbells. So if there are a few dumbbells within a grid of the simulation, you use that to kind of define a coarse-grained stress tensor. And that stress tensor is then included in the Navier-Stokes equations that have been solved by the pseudospectral method. And we use a pretty moderate, I mean, very humble Reynolds number, Taylor Reynolds number, simply because the number of polymers one needs to have feedback and yet give faithful simulations is very large, even at this small Reynolds number. So if you go to larger Reynolds numbers, which in some ways like increasing the box size, you need many more polymers, and things get very difficult very quickly. But even at this small Reynolds number, we do capture the main phenomena which you see here. So what's plotted here is the box average dissipation versus time, and the solid black line is the Newtonian dissipation value. It's maintained constant by the nature of forcing, by the forcing scheme. And what you see now is that for all cases, initially you get a reduction in the dissipation, and then that effect is lost as breakup happens. Most interestingly, you see that the time required for the effect to be lost decreases, or rather increases, as the Weissenberg decreases. So in other words, you have a small Weissenberg number, the polymers take a long time to break, and therefore you have the dissipation reduction effect persisting for a long time. On the other hand, if you take a large Weissenberg number polymer like the blue curve, right? So contrast the red and blue curve. So you take a large Weissenberg, easily stretchable polymer, then you can get initially you get a larger dissipation reduction. You see the blue curve is below the red, but it also breaks up faster, and so you lose the effect quickly. So what this tells us is that if you want some kind of time averaged net drag dissipation reduction so that your overall power benefits are maximized, then you need an intermediate Weissenberg, something like this red curve, the green curve, which gives you significant dissipation reduction, but also lasts for a long time. Okay, so I'll come to my concluding remarks here. So probably one key message here is that these interesting, fascinating phenomena like dissipation reduction, also elastic turbulence, owes their origin to polymer stretching, but they will also meet their demise because of polymer scission, which is a consequence of the stretching. So an intermediate Weissenberg number is this kind of Goldilocks zone where one might want to. Now, talking about elastic turbulence, it has some similarities, of course, to what I've been discussing, because anyway, if you're below the Kolmogorov scale in that bachelor regime of regular turbulence is similar to elastic turbulence. One key difference here is that the turbulence is being driven by the polymer in the case of the elastic turbulence. So as the polymers break, you will lose the turbulence itself, right? So you can imagine that they won't break up to the same extent that it would in high Reynolds number turbulence, because there the turbulence in fact gets stronger as the polymers break. So all polymers break until they reach their smallest surviving fragments. Whereas in elastic turbulence, the moment they start breaking, the flow itself will weaken. So the kind of final state you achieve, I think, will be quite different. And this is something that we want to look at in the future. Of course, these things need to be done for shear flows, channel flows, where the applications are. And maybe these applications we think will benefit from having continuum models that can consistently model Scission, and that's something we're trying to do with the insights we've gained from this individual Lagrangian study. Okay, so a quick advert. So Dario and I are expecting to have a couple of postdoc openings, which will be Indo-French in a couple of months. So if people are interested, I mean, please write to me or Dario. So the postdoc will have the benefit of being in these two very different climates and scenarios while working. All right, so I'll just end with this. So I think our main contribution in this Scission work is the first consistent simulation of Scission in turbulence without numerical artifacts that have been there before, and which also is allows us to predict the final surviving distribution of the polymer mass, to understand the decay rate and how it depends on the Weissenberg number, etc. And our simulations with feedback are able to capture this loss of drag reduction and quantify an effect that was known to people who did these sorts of experiments, namely that you really want a moderately stretchable polymer if you want to be able to study effects like drag reduction and elastic turbulence. So with that, I'll conclude and be happy to take any questions. The Scission work is out in JFM a while back, and some of the work I showed about stretching in random versus turbulent flows is still underway, and yeah, it's something I'm working on with Emmanuel and Dario. Okay, so thank you very much. I'll be happy to answer any questions.
Thanks, Jason, for this really wonderful talk. And are there any questions? I can ask one, maybe. So
yeah, sure.
The first, and then there is one from Prasad. So my question is the fact that the polymers break more frequently in the middle. Does this depend specifically on the features of your flow, or you imagine that this is a general feature? Because I would imagine that it would break maybe more frequently on the edges, because the edges are somehow more exposed to fluctuations, and then in the middle of the polymer somehow shielded by the other springs. Mm-hmm. Maybe here it seems the opposite, that in the middle there is more the transmission of all tensions by the other springs.
Yes, thanks for that question. So actually this picture I've shown you here will help me answer. So the first thing is our polymer is smaller than the Kolmogorov scale, so it's really in a linear flow. So now if you have this polymer in like a linear extensional flow, if the Weissenberg is small, then when it stretches out, it really stretches out in this way. So the maximum stretching happens in the middle, and towards the ends, the extension is less. So this is what happens even in just a laminar extension. So this happens, of course, if you are in a persistent linear stretching. If you have a nonlinear flow, then certainly different parts will get stretched in different ways. On the other hand, if the Weissenberg is large, so that it can get stretched out slowly, then it's much more likely that you have a distribution of different extensions along these springs, and it becomes more likely that random stretching somewhere or the other can break it at a different location. But certainly at small Weissenberg, I think the polymer in this linear flow really behaves almost like it's just in a laminar extensional flow.
Okay, thanks. So Prasad?
Hi, Jason. Very nice talk.
Hi, Prasad.
Hi. Just a quick question. So recently in a work by Dhruba and Marco, you've shown that even with the continuum polymer model, if you go to large enough Weissenberg or Deborah numbers, now these are much larger, around 100 or 1,000, then actually the polymer extension starts to reduce. And that would imply that one cannot think of this purely in a passive way, but the polymer extension has to be looked at as a more of an active mechanism at these high Deborah numbers, where the flow itself, both flow and polymers are interacting with each other. I mean, that's what I think. So have you guys done any such investigations at high Reynolds and high Deborah or Weissenberg number, where both elastic effects as well as turbulence effects are dominant.
Yes, thanks, Prasad. Actually, I saw the paper. I think I saw it last week. I think maybe it just came out then. It's very interesting. Yeah, so I think that this will be an interesting question. What we have done is just looked at feedback at very moderate Reynolds, like I mentioned, just because of the difficulty of doing these individual, I mean, by putting so many polymers. So our Taylor Reynolds was just 50.
Yeah.
And the Weisenberg was increased, I think, till about 4, but not much larger than that, again, in terms of our definition.
Yeah.
So I don't think we can, we've not gone anywhere close to the regime that that you all guys studied there. But that is certainly, I think, interesting. To an extent, what I had said about elastic turbulence, we'll touch on that, because there the feedback is fundamental. So again, there it might happen that, you know, you'll be at this place where the elastic effects create the chaotic fluctuations, but then, you know, that those things break it. So it might reach a very different behavior. So I think that's an interesting regime to think about this problem.
Sure. Yeah.
So are there any other questions? So if not, we thank again Jason for his talk.